Okay, so I want to show you all a neat little algebraic trick. This is something that, again, I like to call back to my own undergraduate days as an undergraduate second major in physics, and I use the following trick a lot. It was very, very useful for me. I hope it will be for you as well, and it relates to some of the things that we've been talking about. So here we go with it. This is a discussion that has in the past been a think, pair, share exercise in live classes, but here we are. So the question is how would I write e to the ax sine bx as a linear combination of these two functions, e to the rx, e to the r bar x. So the way we go about dealing with this is to recall that we already know some relationships between these things. So let's start by writing down what we know, and then we'll figure out where to go from there. So here they are. I have these formulas, right, for e to the rx and e to the r bar x. Very important to know these formulas, this one in particular, of course, but again, this one comes up significantly as well. Having written those down, we realize that this thing that we want to solve for is right there. This is almost like it's a little 2x2 system of equations, and you can just solve for what you want. In particular, we would take these two equations and subtract them. Right, subtracting on the left side gives me that. On the right side, subtracting makes these cancel. And these over here, when you subtract, reinforce, thus giving me that. And then it's just a matter of moving this 2i over to the other side of the equation, and we're done. So it's very quick. I did, by the way, after dividing by the 2i from there, rewrite these by a little bit of complex arithmetic. Don't forget how complex arithmetic works when you divide. Right, you can multiply by the conjugate is a nice way to think about dividing. Here you can just take both sides of both top and bottom and multiply by -i, and that gives this. And then likewise over here. Okay, so handy formula to know. And then analogously, if I wanted instead to solve for this, well, then I would just add, making these cancel instead of subtracting. And as a result, skip the algebra. Y'all can fill in those blanks for yourselves, and you get this formula. Okay, so these are a little bit surprising formulas, but they're also very, very useful. And what I want to point out about why these are useful, it's because these formulas allow us to take expressions that are what I'm going to call algebraically hard. They're not trig functions. They're not exponentials. They're combinations of trigs and products of trigs and exponentials, which are algebraically hard to deal with. And we can turn them into just plain old exponentials, which are very easy to deal with in many cases, and very easy derivatives, very easy integrals. And this is a big win. Okay, so I'm going to show you some examples of how this can be useful on the next page. Again, complex exponentials are easier to work with, is the point here. So let's think back to Calc 2. Look at this integral of e to the ax cosine bx. You may have had to, at some point in the past, crank out this little bear of an integral. The way you do it is by integrating by parts, but sadly you have to integrate by parts twice. And then once you've done integration by parts twice, you're still not done. Their same integral appears and you move it to the other side, and a little tricky business. It's really quite a pain to do this. Various constants show up, lots of minus signs show up in dealing with the integration by parts, and it's annoying. Okay, well, by virtue of the algebra on the previous page, this is that sum. And so I can translate a hard integral involving exponentials and trig into two easy integrals. They're just exponentials. Integrals of exponentials are easy, right? Look how easy. This is that, this is that, and we're basically done. Not quite, of course. I do have to multiply that out, and there's some common terms, canceling, and a little bit of complex algebra. You've got to do a complex arithmetic here. Multiply and divide by the conjugate of r, to, for example, to make this fraction work out. But not that big of a deal. Okay, certainly I think this way adds up to a much easier way to solve the problem, in my opinion, than this one, which I think is hard. Okay, now here is a related fact. This e to the ax cosine bx that we were just looking at. Another way to think about that is it's the real component of e to the rx. That can be observed up here. E to the rx, you see right there, it is the real portion. Or coming down here to this formula, these two functions have the same real portion. So again, it immediately follows that this is 1/2 plus 1/2, namely 1 times the real portion. Okay. So having observed that, this is morally equivalent to the algebra above. I can turn an integral of an ugly function into an integral of an easy function, just by sort of recognizing that I'm looking, of course, only at the real portion, and real portion of an integral is the integral of the real portion. So integrals are done what you might call component-wise in the complex plane, another way to say that. And so again, now I'm going to work out the rest of the details on this, but notice the integral itself. It's a one-liner, right? No fancy integration by parts, nothing annoying like that. The only thing that is a little, again, sort of tedious, I guess you might say, that fraction you need to rewrite. But again, no big deal. You multiply top and bottom by the conjugate. There it is. It's not that big a deal, right? Euler's formula allows us to rewrite that in rectangular form. Not that big a deal. And then it just boils down to multiplying out, sort of foiling out, if you will. And you'll notice that real times real gives us that term. Imaginary times imaginary gives us that term. And we are done. Not that much trouble. And we avoided a tremendous amount of algebra just by instead thinking of it that way. Okay, so I hope you'll find this useful. I certainly did, and most of y'all are engineers, and so engineering is not that different from physics. I think you're going to find these tricks to be very useful. Okay.